So before I start, a few quick announcements. First of all, maybe this is probably warrants a post to Piazza at this point. Maybe one of either I or Tiaz will do it. So first of all, the Homework 5 will be out next Wednesday, not today. The reason for that is that it will have potentially, we're trying to actually get Autolab, making sure Autolab still works with it, to have a question on probabilistic modeling, and therefore it's a little, it's hard to, probabilistic modeling and MapReduce, which are both taught next week, and so I wanted to make sure that we had time to actually talk about those things. And the other thing, and so this does mean that it will overlap a bit. We still have time in the semester, but it will overlap a bit with the time you should be working on your project. What that means is, take the next week to work on your project. Definitely, the next week or so should be focusing on the project, kind of getting that underway. And then the other thing about the next homework is it will actually, as I mentioned last time, have some of the problems are optional. So you can sort of pick 2 out of 3 or 1 out of the 3, depending for the 388 or 688 versions. The other thing is that the tutorials were released yesterday. Several people, so the TAs posted, several people have issues with their tutorial, how it showed up, and this is just sort of life when you submit a lot of tutorials. Some are going to have issues with the viewer. If your assigned ones are not, so don't probably wait a little while before you do your assigned ones. They are due next Friday. It's not this Friday, but the following time, so you have plenty of time to do those. But the TAs will send out all the forms for that shortly if they have not already. I think that was the 2 main things. So any other questions about the homework or anything like this? Logistics? Okay. Okay, so let's jump in. So today's lecture is kind of another kind of one-off lecture like the last one and like the next few, actually, about a topic in machine learning, which is very sort of popular these days. In particular, we're going to talk about deep learning. And this is a little bit different from how I teach deep learning. I mean, it's actually a lot of similar content, but it's a different level in how I teach deep learning in like a machine learning or an AI course. And then we're really not going to go into any of the detail of the algorithmic development. We're going to cover things at a pretty high level. And the reason for that is that although deep learning is becoming more and more prominent, I think its role in data science is still to be seen, mainly because a lot of data science doesn't need models that are as complex as deep learning. This is what I sort of mentioned at the beginning of class. But undeniably, and I'll focus on this a little bit, there are domains where you do want to incorporate deep learning techniques. But for the most part, you actually can do this without a huge understanding, I think, of how the algorithms work internally. You can kind of do it at a pretty high level. Now, there are some tasks where you still do need to sort of integrate deep learning in a very fundamental way. But I think there are a lot of cases where the kind of things I'm going to talk about today actually work surprisingly well. And one of those potentially will be something you work on in the homework. Okay, so let's just jump right in. What we're going to talk about is we're going to first talk about the history of deep learning and machine learning. Talking about machine learning with neural networks. For the most part, the deep learning, the term kind of predated neural networks. These days, when people say deep learning, they just mean multi-layer neural networks, usually very structured ones, in fact. We'll talk briefly about training these things, but I won't talk in any detail about how you really compute like the gradients in this case. That's actually can be quite complex, or at least worth another lecture at least, so I can't really cover all this in one lecture. Then we'll talk about some specialized networks like convolutional or recurrent networks, again at a very high level. And finally, we'll talk about this notion of where deep learning fits into data science. Because I think for a long time, it was sort of seen as being separate, right? Data science is much more about the interpretability we talked about last time. And deep learning is kind of the epitome of uninterpretable models in some sense. And so I'll talk about where I think deep learning does in fact fit in. Okay, so let's start off by talking about some recent history of machine learning. This slide's actually a few years old. It's actually a good slide to include in a data science course because I created this slide and I can't create new versions, or I haven't gotten around to creating new versions because Google Scholar broke my scraper. So I have not gotten around to generating new versions. This is up through the end of 2015. And what I did here was, for all these years, I took the number of times the word machine learning appears in the title of a paper versus the number of times that neural network appears in the title of a paper. So this is a ratio. It can be more than 1 or less than 1. For the most part, it's still, maybe these days it's over 1, but for the time I generated it last, it was less than 1. But what's interesting here is it sort of tracks pretty well the popularity of neural networks in machine learning. Okay, so this is a ratio of how often neural network occurs versus machine learning. Now, of course, it's kind of a bad metric because Even though I work in machine learning, I don't put the word machine learning in many of my titles, nor do I put, I guess I actually have a few where I put neural networks in my titles, but it's definitely imperfect, but I think it works surprisingly well, actually. And there are a couple of interesting milestones here. So neural networks, the history kind of goes like, in the late 80s, early 90s, the backpropagation algorithm was proposed. It was actually proposed many years before, but kind of simultaneously rediscovered by many people and really advocated for in the late 80s. That got neural networks to be very popular in machine learning for a while. And by the early 90s, neural networks were kind of like the method to use in machine learning. However, at the time, we didn't really have the compute or the data that really made these things that useful yet. And so other methods, namely support vector machines and boosting, kind of dominated the latter half of the 90s. They were became popular in 95 and really kind of decreased interest in neural networks and these models after they came around. I started publishing papers in 2003, which was at the absolute lowest point of neural network popularity since the 80s. And so it's sort of amazing to see. I mean, this has all happened since I've been involved in the field, right? Through no actual influence of my own. I was a very latecomer to this, in all honesty. But it's been kind of amazing what's happened since then, right? So there have been a few sort of notable milestones here. So I remember, I think the NIPS conference in 2006 was when I first started hearing people talking about the term deep learning. At the time, it was actually due to the fact that people were talking about pre-training networks based upon unsupervised learning, which was sort of brought back a lot of these ideas. But it turns out you don't actually need any of that stuff anymore, so no one does that anymore. But that idea historically was interesting. The one big milestone that everyone kind of points to as, which we'll mention in a second, which everyone points to as kind of kickstarting the modern era of deep learning, was the success of the AlexNet deep neural network in winning an image classification contest. This created a huge amount of popularity in the field and really transformed the field of machine learning. That paper from 2012, I should say the end of 2012, so it's less than 6 years old, has about 20,000 citations right now. So this really was which is not bad for a 5-year-old paper. This really was the dawn of the new era in machine learning, kind of looking back. Now, you can argue with that a little bit. People would say, oh, there was some other papers that happened around the same time, but it really was this turning point, and I think it's sort of worth emphasizing that. And then soon after, you had things like Google buying DeepMind for $400 million or so, with about 40 employees at the time. And at the time, everyone thought it was crazy, but it seems to have worked out pretty well, right? DeepMind's done some pretty cool stuff since then. So it's really been an amazing kind of ride in the last few years in the field of AI. And I think it does beg the question about, look, this is clearly happening. Where does this fit into the story of data science? Because this seems not quite like data science. These seem like much different, more complex models. So where does it all fit in? Let me dive into this a little bit more, though, and talk about actually one of these things, which was the AlexNet model. So I forget when it started, actually, but for several years before 2012, like a couple of years before then at least, there was this image classification contest. So going by the name of the image, I forget the full name of it, but it was essentially known as now the ImageNet contest. Basically, there was this large data set of images with labels to them. There's 1,000 different labels, dogs and cats and boats and stuff like this. And you had to classify which type of object was in each image. And the AlexNet network was a convolutional neural network, which we'll talk about that in a second. But it was a neural network that got a top 5 error rate. That means that you can get 5 guesses, and if one of your guesses is correct, you get a point. Otherwise, you don't get any points. But a top 5 error rate of 15%. So that means that in 85% of the examples, the correct answer was in the top 5. This at the time was a huge improvement over the state of the art. So the next best system that was not using deep learning, it was using some other very, very hand-tuned computer vision-based system, got 26% error. And you typically don't see jumps like that very often in the history of machine learning, right? The history has been kind of, and computer vision was slow and steady progress for a long time. all of a sudden you had this amazing jump. And actually, I remember talking to the person that ran that contest about when she saw this entry come in and said, "Whoa, this is interesting here," and that was actually a pretty impressive moment in the history of machine learning. So I should say, since then, we've also improved that substantially. So now it's less than 3% the error, to the point where actually this contest is no longer being run this way anymore, because it's just people feel like we've gotten all that we can out of this contest. Something that was thought to be a grand challenge just 6 years ago is now kind of being at least substantially changed, because this part of this pure classification task is just not interesting anymore. We can look at some of these things that it predicted. So here's some of the pictures in ImageNet, and showing the 5 predictions that AlexNet made on these images here. So look at that image. So it's a mite, that a container ship, that a motor scooter. It gets this one wrong, but this is a pretty reasonable thing to get wrong. I think it's labeled as a cherry because there's cherries in the front, but it calls it a Dalmatian because there's also a Dalmatian in it. And then this one, this is a Madagascar cat. It calls it a squirrel monkey, but I wouldn't have known that, right? So it's pretty impressive. Now I should say, this looks like there are only 1,000 classes, so this is looks like a very random assortment. There's been a lot of training examples it has, of course, of Madagascar cats. So they can do better now than this, but it's still sort of amazing what these things are able to do. Remember, all they see is this collection of pixels. They don't see any structure to the image. This has been a grand challenge in AI for a long time, and we've really made this amazing breakthrough in the past few years. Similar kind of breakthrough. So people have probably heard about AlphaGo. A few now 2006, so more than 2 years ago now. A Go playing program based upon again a deep neural network, a deep convolutional neural network beat the world master in Go. And I think a fun comment I heard at the time was that so it beat him 4-1, and a fun comment at the time was that although it seems bad that he was the first person to be beaten by the computer, he's also the last person to ever beat the best computer in the world, because now they've improved this even more, and so he actually was the last person to ever win a match against the best computer playing Go. So I think that's actually very cool for him. The last example I'll say is Google Translate. So in 2016, Google Translate switched over from their sort of much more data-driven system to a system based almost entirely, in some languages at least, on recurrent neural networks actually. And there's a really interesting New York Times article about this. I recommend everyone check that out if they want to read a little bit about this. It's a really nice story too. But basically, sort of overnight, we switched from translations like this, which if you read it is fine, but not, you can get the sense of what it's saying, but you can't really, to things like this, which basically look exactly like English, right? And so it's sort of really impressive what's happened here. Now, I remember when Google Translate was kind of this game of you could kind of figure out what it meant, but it was sort of like a game of trying to figure out what it meant, right? It was an exercise. You could get good at it, in fact, but now you don't have to. For a lot of languages, at least, not all of them. Some of them are quite bad, but some of them are, for some language pairs, its translation is sort of amazingly good to the point where it looks just like real translations. Okay, so what's underlying all of this, and what roles to play the material of this course? So I want to talk now a little bit about machine learning with neural networks and dive into it a little bit, because I can actually explain some of the basics using just what we've talked about in class so far, but I won't dive into it too much, of course. So the term neural network, as we sort of, as we say, right, every machine learning algorithm is 3 things. It's a hypothesis function, a loss function, and a optimization procedure. But with neural network, it actually really just means the first one. So neural network itself is a hypothesis function. It's a way of making predictions from inputs. And then the loss function and the optimization part are usually kind of implied. And there's common ones, but they are not all, they don't have to be that way. It can still be a neural network with just the first thing. So again, going with this pattern of us being very good at coming up with catchy names in machine learning, neural network sounds very catchy, but not being very precise here. it really just means the first element. And so you have to know that the second two elements, when someone says a neural network, you have to understand, what their architecture is, what kind of hypothesis function they're actually using, this which is a neural network, then plus what loss function they're using, plus how are they optimizing it. The optimization is usually just stochastic gradient descent, so those are actually pretty well implied. But it basically means nothing to just have someone say, oh, we use a neural network to classify this, and they got this accuracy, right? Without specifying the structure of it and the actual how they solve, what loss they use, how they solve this problem, it really means nothing. So be aware when someone says neural network, you have to specify what they actually mean by that. Okay, so the way I'll motivate neural networks is in contrast to traditional features in machine learning. So in machine learning for a long time, as we've sort of discussed so far, right, the performance of an algorithm or how well you perform on a task will depend a lot on the features you choose, right? So in the bus prediction task that you worked on or are working on, I forget if there's another one in the SVM. I don't think so, no. The spam, I guess the spam has some features you can engineer too. So in some of the homeworks, right, you found that the features you choose have a very big impact on your performance you actually get from these classifiers. And the sort of the history of machine learning to a large in applied fields like computer vision or speech or things like this is that every 10 years or so someone will come up with a new set of features. So we'd have in computer vision you have SIFT features or HOG features. They had great names for these things too. Don't worry about those at all if you haven't heard of those. But every 10 years or so, and in audio you have things like MFCCs. I don't even remember what that stands for. But basically, we would just make these exercises in different domains. We try to find new features that when you use those features with an SVM or a linear classifier of some kind, they give you good performance. And so the key question, and so the performance really depends of, say, a linear classifier, depends crucially on coming up with good features to actually put into that classifier. And so this kind of raises the obvious question, right? So we're really good at tuning parameters of our algorithm. Can we also, of learning these parameters from data, can we also come up with an algorithm that will automatically learn the features themselves? So can we learn both, for a linear classifier, can we learn both the thetas, the weights, and the features themselves? Can we go about doing that? So I'm going to give sort of one take on this. Let's do this, give a first try, which for those that are curious, this will not work out this first try. But let's give it the first try. And let's think about a set of linear features that sort of capture. Basically, we have one linear function that gives us our features, and the linear function that gives us the actual classifier. So our classifier, let's see, DocCam, will be something like. This is very h theta of x, theta transpose x. And in fact, I'm going to, for this one, because it's more common here, I'm going to use the terms W for weight. So I'm actually going to say this. I'm going to refer to H as a set of a lot of weights here. But actually, this is going to equal not this thing, but W2 times our features of X plus maybe a bias term. We're actually going to make our bias terms, our constant terms, explicit here for kind of historical reasons. But you'll always see this, so I want to write it this way for neural networks. Okay, so the key part here is that this is going to be our linear function. This is a linear function, right? Actually, W here is a row vector, in fact. But this is a normal linear function. It's sort of our standard form. And we're also going to set our features here to be some other linear function of our input. All right, so it's going to be some matrix W1 times X plus B1. So does anyone see what's the problem here if we were to do this? I haven't really described it, so it's no problem if you don't see it. But this is sort of one thing you could do, right? So use one linear functions have treated us well so far, right? So let's use one linear function to create the features, another linear function to predict based upon those features. So what's the problem here? Yeah. Okay, so too slow. No, we're going to get much, much slower in a second. So that's not actually the problem. Yeah. Yeah, exactly. So that's the actual problem here. So if you write this out, this is just W1 times, so W2 times W1 x plus B1 plus B2, right? Which is equal some W tilde x, which is just this, where W tilde here equals W2 W1 plus B tilde, B tilde, where B tilde is equal to W2 B1 plus B2. So basically, we're right back at a function, hypothesis class, that is exactly linear in our inputs, which is what we didn't want. That was what we're trying to get away from, right? So if you use a linear set of features and then you apply a linear classifier, it turns out there's no added benefit from just applying linear classifier directly to the input features. You don't gain any representative power. Okay, and that's the problem with this tact here. But it turns out, even though you can't do this, something very, very similar does work. And so in fact, I guess this is what I said here. We sort of draw these networks like this, but the problem here is that this classifier here is just equal to another linear classifier, the same as we had before. So this doesn't work, but it's very close to something that does work. And so to make this work, we're just going to do one thing. All we're going to do is we're going to add nonlinear functions after these linear operators. So I'm going to take this one here. I'm just going to add a nonlinear function there. If I want, I don't always have to do it at the very last layer, but if I want to, I can add another nonlinear classifier there. Where a common set of choices for these nonlinear classifiers are things like and don't worry about the specifics here, but things like the hyperbolic tangent. That's defined like this. It looks like this. It varies between -1 and +1. The sigmoid, which we've seen before actually, which varies in the context of logistic regression, which varies between, its output is between 0 and 1. And the actual most common one these days, which is called the rectified linear unit, which is a fancy name for just taking the max, just clipping x to be 0, the max of 0 and x. So if x is negative, you do that. Now when I write this, what I actually mean is I mean this function here applied to each element individually in the vector. So this whole thing is a vector, right? W1 is a matrix, so you multiply this matrix by a vector, that gives you another vector. When I say we're applying this function, I mean we're applying this function kind of element by element. So we're just taking every single element in that vector, and if it's negative, we just throw out the negative. We just set it to 0. Okay? In the rectified linear unit, for example. And what's kind of amazing here is that if you just do this, which seems like doesn't seem like that big a deal, right? All you're doing is you're doing a linear function, but then I'm just clipping it to be positive. But it turns out if I do that, I actually come up with functions that can express any arbitrary function of the input. We won't prove that, but it is in fact the case that neural networks with enough, with a big enough sort of vector there are called universal function approximators. They can approximate. So let me just say a few more things here. So we typically draw neural networks something like this. Actually, when you have lots of layers, you won't even bother drawing individual neurons. So just draw like a big box for one layer or something like that. But notationally, what I'm going to say is I'm going to use the terms Z to represent the intermediate layers in this network. Those are the intermediate things like this. So I would call this, for example, something like Z1. The big important part there, and these are called either sometimes the hidden units or the activations of the network. People use all these terms at different times. The point, though, with all these things is that these elements here, these intermediate elements in the network, they are not ever observed. We have no real sense of what those should be. These are just, think of them like the features, right? We don't know what the features should be because the features can be equally good. So some features could be just as good as other features. You just end up having a different sort of weight vector, different final linear function of the features of the last layer. But you could learn different representations, different sets of features that would still work just as well just as well. So there's nothing about the data themselves that specifies what these features should be. They are purely learned, and they are learned in a way to actually enable us to get as good performance on the full task as we can. Okay, and so in reality, actually, what these things are can be very hard to interpret, but they sort of in some sense are just things that the algorithm uses to get the performance as good as it can be. Okay. So I should mention this before. So it turns out that a network with a single hidden layer actually can be what's called the universal function approximator, in that it can actually approximate any function over the input. So again, what this means is that whereas before, if you just had linear layers, you were constrained to only make linear predictions of your input. If you add this one little trick, right, of just clipping the negative entries of those intermediate features, you actually now can represent any function over the input. Again, with a big enough set of hidden units, but you can represent any function. It's kind of an amazing property. Now, it's also the case that this is not that relevant of a property, because it's also true that like polynomials can represent any function. In fact, so can radial basis functions. So this is more a property of kind of the, and so can nearest neighbor methods. Actually, really anything, decision trees, whatever, right? They can all represent, actually most of them can represent any function. So this is actually not that relevant from a practical standpoint, this sort of universal approximation guarantee. But it's still good to know that we do have a function class that's sort of very powerful in practice. But what really matters, of course, is just that not just that it's sort of we have this mathematical property, but that they actually seem to work very well in practice. Now, a few quick caveats here, though. So with this change here to this architecture, the final optimization problem of minimizing a sum of losses with respect to our parameters, and our parameters here would include, all the weights and what are called the biases, so all the constant terms and the weights. All of these things, when you consider the parameters being all these things, our optimization problems are not convex functions of these things. In other words, there are local optima. So you don't expect to find a set of parameters for your neural network that is globally optimal. You have to actually sort of optimize it and hope it does sort of well enough. This was, I think, considered to be a very, very big problem of the methods for a long time. So for a very long time, people kind of dismissed, and this was in those 90s years, people kind of dismissed neural networks because of this problem. It's that we wanted to have architectures where we could guarantee that they would find the global optimum when we optimize them. But the current thinking is, and there's a lot of actually sort of theoretical work here, but the current thinking, I think, is that, well, even if you can't find the global optimum, if in practice a local optimum or however we optimize these things appears to work better, it's still the way to go, despite the fact that we don't have guarantees of global optimality. The other big caveat here is that even saying this is actually not enough to specify a neural network. So what modern deep learning actually does is it has very complex constructions of different networks. And I'll show a few. You actually saw one already. I don't think I'll actually show many more because it would take a little bit too much time. But you saw one already. So this is actually different layers in the network that I was showing on the AlexNet architecture. These are what are called convolutional layers, which we'll talk about in a second. These are just these dense layers, which are the things I'm talking about here. But this is a pretty odd and seemingly kind of ad hoc choice of architecture here. Why did they actually design this? Design it this way? And this is actually a real problem with networks. So the choices of architecture actually do matter a lot, and they'll have a huge impact on how well they work. Okay, so this is sort of the definition of neural networks. I'll go back to the thing there. I don't have too much more math for this lecture. This is the definition of neural network. Now, on some level, what the term deep learning, at least as it's used in current, the current vernacular, is basically just means multilayer neural networks. You could argue this actually. You could say that deep learning somehow means it's just really about deep multilayer models, but things like probabilistic models also fit that framework. that's fine. I actually wouldn't argue that point one way or the other, but I would say that 99% of the time when people talk about deep learning, they just mean deep neural networks. What this means is instead of sort of one layer of a network, you have multiple layers. So what that means is you create some features here, a linear function. So this is your input. You create some features here, which are linear combinations of those things, plus this nonlinear function applied element-wise. But then rather than just predicting your output from that directly, you use those features to create another set of features. Again, form a linear functions of these, clip the things to be non-negative, do it one more time, and then finally make your prediction at the very end. And the vast majority of current neural network architectures are these sort of deep architectures that have multiple layers in them. Now, the obvious question here is sort of why do we want deep networks? We just found out that using a single hidden layer was enough to represent any function. So why would we actually want to use deep networks? And there are actually a few answers from this, which I think none of which are very satisfying except for the last one. So the first thing is, again, what I said before is that this universal function approximation was a great point in theory, but isn't that useful in practice because every type of machine learning algorithm, or lots of them, are also universal function approximators, and so this property wasn't that great by itself. And so a nice example in this case is from things in circuit theory. So this is a sort of standard domain in computer science, but all that you have to worry about for now is there are certain functions. One example is the parity function. So this is if you have a sequence of bits, determining whether they're an odd or an even number of ones in your sequence of bits. This function, if you were to compute it with a single layer circuit, which is kind of like a single layer neural network in a lot of ways, it would actually take a feature size of 2 to the n. But if you allow yourself to have a logarithmically deep circuit, you can actually do this in just order n number of features. And the way you do that basically is you sort of compare parity of 2 bits at a time and kind of like a tournament, and then your last one works, and then you compare the parity of those 2 things, and you do it kind of hierarchically. And this requires only a number of features that is linear in the total size of the input, as long as you can have just log n different layers. Okay, so this is a nice example of a function that is easy to compute with a deep network. In this case, it's a circuit, but you can think of that kind of like it shares a lot of similarities with a neural network, but which is hard to compute in a shallow network. The problem is the parity function is notoriously hard to learn. Actually, we're really bad at learning parity functions. That's one of the things that still trips up almost all deep learning algorithms. So it's not like we're learning things that have that exact kind of structure to them. So I don't really buy this argument. I mean, I think it's nice conceptually, but I don't really buy it. I don't think it's a matter of there being functions that we can only express with deep networks. I think that there's this sort of, whatever it is that we can learn is not this. So this should not be our example of why we prefer deep networks. The other thing people always, or not always, but sometimes refer to is the structure of the brain. And if you take away one thing from this lecture, just know the fact that the neural networks are not like actual neurons in your brain. And so if ever you see anyone say that neural networks work like the brain or anything something like this, you know they don't actually know what they're talking about. So, so people sort of say, okay, look, the brain has many layers in our neurons. They have many connections before sensors. Light hits the sensors in our eyes and goes through many different neurons before it goes to wherever we want, wherever in our brain figures out where what the actual object we see in that image is, and that sort of implies in some sense that also maybe our models should be deep too, and that also, I mean, again, just like the first one, there is actually some validity to that. We have an existence proof, in theory, of a system that actually does use multiple layers to do pretty amazing things in our brain. But the truth is, we really don't have, there's definitely no correspondence between how modern neural networks work with things like the ReLU activation functions and how the brain actually works. It's an incredibly kind of tenuous connection, and it's a great marketing term, but it really has no real basis in reality. We don't know how the brain works yet, and so again, trying to justify our choices here based upon something that we don't understand and can't learn seems a little bit tenuous. So the reality is that the only real reason to use deep networks that I'm really comfortable saying is that they seem to work really well in practice, especially when you have things like images and specialized layers like convolutions. When you apply many of these things together in a long series, this seems to give results that are far better than anything we can do with non-deep architectures. And this is why we use them. They just are the best thing that we have, the best tool we have right now. Okay, so I want to actually make one more point before I have a quick poll on these things. But the other point, which may be the other thing you'll remember from this lecture, is this question of sort of why is this happening right now? Right. So why is deep learning so popular right now? And because after all, I mean, though there are some advances, for the most part, we had all these things in the late 80s, right? The techniques that we're using now are kind of the same as what we used in the late 80s. And so why is the revolution happening, and why did it happen in 2012? Why not 20 years before then? And I think that there's a few answers to this that are worth emphasizing. So I think there are three things that are coming together right now that are making this possible. The first one is that we do have better algorithms and models. So we have constructed a set of better architectures and algorithms for optimizing the architectures than we had 20 years ago. Not in all cases, but in most cases we certainly do. And that's important. You can't actually, people often dismiss that fact, but I think it's actually important to mention that there have been some notable improvements just in the algorithmic side of things. But it's also impossible to deny kind of these two even maybe more major factors that have been transforming the field since then. The first of which is that we have a lot more computing power than we did back then. So these are, I mean, getting to your point maybe before, a point that was raised before, you know, these are big things, right? A matrix multiply is a lot more expensive than a vector multiply. This seems like these are really complex models, and they are, in fact. These things are very, very compute heavy, and we're only being able to solve them these days with basically using lots of GPUs to solve a lot of hard problems that were GPUs were just sort of well suited to problems like this in machine learning. In fact, I mean, that network AlexNet you saw, one of the notable things was implemented on a GPU. So it's one of the first very large-scale GPU-based machine learning, deep machine learning algorithms. And again, there have been some things before them, but it was really one of the first ones that became well known. So computing power has been very important here. And the third thing is the amount of data. So these models, they are high. They have very high capacity. In order, that means they have high representational power. But in order to sort of to use that capacity well, we need lots of data to train them. So it really is these things kind of coming together right now that are making this possible in the field of machine learning. And if the analogy I like to give for this, and this is another thing you can, a nice sort of point to give to other people if they ask you a similar question, is I use the analogy of an airplane for this. So you can think of the compute power as like the big engines of the airplane. The data is like the fuel of the airplane, and the algorithms and models is like the aerodynamic design of the airplane. So without any one of these things, it doesn't really work, right? You can put a big engine and a lot of fuel on a building, and it won't really go very far. You can have a great airplane and a lot of fuel, but if you don't have any engines, you're out of trouble. And similarly, if you have great engines and nice aerodynamic design, but no fuel, you won't go very far. And I think it's actually a pretty good analogy. And it's helpful for people to understand, especially in other areas when you're explaining, as a data scientist, some aspects of deep learning, which you probably will, just because it is becoming so prevalent right now. This is a good analogy to use for explaining the current evolution of deep learning. Yeah?
How do you decide on the number of neurons?
I mean, so the question was, how do you decide the number of neurons in a layer? We're not going to get into that at all. There are lots of answers. The fact, though, is it doesn't really matter that much. What you should do is you should pick a large enough thing that the thing can work well, and then talk about regularizing until it doesn't overfit too much. So you pick a lot of units. People just use like powers of 2 a lot, so they pick things like 256 or 512 or whatever, or powers of 10. And that seems to work pretty well. The key actually is how you regularize them to prevent overfitting. All right, so let's have a quick poll on this right now. So actually already, I think we've covered enough that you can answer a few questions about deep networks. So here's this, I mean, these are all, oh, shoot, I just realized I don't think I made this multiple choice. I'll edit it to make it multiple choice right now. Ooh, what happened there? Actually, that's strange. Let me actually edit the question to be a multiple choice. This is going to be a multiple choice question. It's, multiple answer question. It says, what advantages do you expect to have if you apply a deep network to some machine learning problem versus a pure linear classifier? Let me edit this actually to immediately make these things multiple choice, and then I'll open it. Do you expect there to be of applying a deep network to some machine learning problem over pure linear classifier? So that means linear in the inputs themselves, not in the feature, not in some features. Less chance of overfitting the data, can capture more complex prediction functions, better test set performance for a small number of data points, better training set performance for a small number of data points, and then better test set performance for a large number of data points. Okay, so most people, okay, so less chance of overfitting data. Most people said no to that. That's correct. So the point here of all of this is that it actually has a bigger chance of overfitting the data. The point of all this is that deep networks are higher capacity models than a linear function. So that means they have many more parameters. That means they can fit much more complex functions. But with that potential to fit more complex functions, there also comes more ability to overfit to training data, right? So I'll also mention this in the next few, but if you only have a few data points, there's a very good chance you're going to overfit to your data. The next two are also right. So most people correctly said that it can predict more complex functions. That's good. I'm glad I did emphasize that part. I always wonder about like the only 90, the 10% or so that say no. But I guess people are trying to get in their answers quickly. But yes, that's the point of what I sort of said earlier, right? The point of this in some sense is that we can represent more complex functions. You can represent any function as opposed to just linear functions over your inputs. Better test set performance for a small number of data points. Again, that's probably not going to be an advantage, right? Because when data points are small, you probably don't need the capacity of these models. You don't need that representational power. And so, as people correctly said, you're going to probably not get this benefit from a deep network. This one's kind of the tricky one, actually. So most people said no to this. Better training set performance with number of data points is small. But the important thing is training set performance here. So you actually will get better training set performance with a deep model, with any more complex model. You can always fit your training set better, right? So this is sort of the model complexity curve we had that would keep going down with more complex models, regardless of the data set size. And eventually you hit 0. You get perfect performance. But on the training set, sure, you can do really well with small data points. You can fit them all exactly. Maybe you can't quite fit them all exactly with a linear function, but you can fit them all exactly with a neural network. But the point, though, of course, is that maybe people are picking up on is it doesn't really matter, because who cares about training set performance? You don't care about that. I mean, we can get perfect training set performance by just memorizing our data. It doesn't really give us any real benefit. What we really want is test set performance, and people sort of correctly got that there is no advantages in test set performance. And then finally, this last one, yes, you do get better test set performance, of course, though. This is what you really care about, with a large amount of data. And this is what I emphasized on the last slide about this sort of needing lots of data to train the model well. So again, in kind of the curve, we would see these examples of model complexity. Well, there's actually two that are relevant here. So the first one that's relevant is this curve of model complexity. And this is going to be, error. And on the training set, it's sort of, you get more complex, you just keep going down and down and down. And then the test set, you increase them like that, right? But the other curve that's important is the performance of these models as you get more data. So another curve looks something like this, which is the amount of data. So this one will be test, this one will be train. The amount of data, if that's on the x-axis there, when you start off, you get really bad test performance, but eventually it goes better and better. When you start off with training, it actually gets really good at first because you can overfit and just do really well. And in the limit, these two things will actually converge together. And so for lots of data, a more higher capacity model will actually do better. We'll talk about these curves more actually next, or a week from Monday, I think. Okay. All right. So having said that, let me move back to the rest of the slides here. Okay. So I want to describe very briefly now how we train these networks, because really, I'm doing this mainly because you actually already know how this works. It's just the same techniques you've used already to train gradient descent for linear models with one little twist. So again, our neural networks for machine learning setting is we have a neural network with a hypothesis function. Our loss function is something kind of traditional, like binary classification. We'll use like a logistic loss. And our optimization problem now is to minimize over our theta, where theta now corresponds to all the weights in the network. So the W's and the biases, the W's and the B's over different layers. How do we actually solve this problem? And the way people do it is with a method called gradient descent. So it's not the same as what you've seen, but actually they use a little variant called stochastic gradient descent. So let me talk about what that means. So the big challenge for networks here is that we very often have a really large number of samples, right? We actually decided we needed lots of samples to do well with these things. So imagine the case where you actually have an infinite number of samples. The way you compute our gradient, right, the way that we're used to, is we sort of take we compute the gradient with respect to our parameter of the loss function, which means we basically compute the gradient of the loss at each example, add them all up, and then take a small step in that direction, right? So if in the limit, right, where we're going to have infinite number of, and this is just the formula for the gradient, gradient descent as we've seen it so far. So there's a problem here, though, right? Because in the limit, as we have more and more data, it will take us forever to compute this sum. So by the time we computed all the gradients over all examples, we're out of time. We haven't done any work. We haven't taken even a single gradient step yet, and we haven't done anything. Okay? So this sort of seems odd, right? Because more data should be good. It shouldn't be bad for us. More data is good. Why would it hurt us to get more data for computing our gradients? So all that we really do in stochastic gradient descent is that instead of computing a gradient on all the examples and updating our parameters based upon that gradient, that sort of average gradient over all the examples, we instead compute gradients on our examples one at a time. And we take smaller steps in sort of individual gradient updates for each example. Okay? So let me actually give this a little bit more detail. Our algorithm for gradient descent, again, this is sort of writing it out. There's, of course, matrix forms for this, but matrix form is just doing this kind of quickly with matrices. But our algorithm, in some sense, is sort of, we compute the gradient for each example, and then we add them all up to get our update, right? We add up all these gradients to take our update. In stochastic gradient descent, we actually don't do that, and we repeat that whole process, right? That's normal gradient descent. In stochastic gradient descent, we don't do that. Instead, what we do is we repeat the following. We iterate over each example in our data set. And of course, if you have infinite data, this is fine because you just iterate forever here. You never run out of data. But for each example, we actually take a small step in the gradient just on that example. Okay? And so the important thing here is that in the top version, which is normal gradient descent, we don't make a single update to our parameters until we've computed the gradient for every single example, the gradient on every single example. Whereas here, we make an update even after seeing just the first example, or the second example, and the third example. What this means is we can actually just benefit from having more data, right? Because we don't need to sort of pay the cost of averaging things over our entire data set size. And it turns out this works actually very well. It actually sometimes works better than the first one because it injects some, especially for these non-convex models that have local optima, it injects some noise in the process, and so actually it even works better than the first version. But the real reason why we do it is it's much, much faster than the first version would be. And I should sort of mention in practice, you actually don't do one example at a time, you do a small number at a time, and compute the average gradient over that small number. That small number of examples is called a mini batch. And so this is the standard way everyone will train deep networks. So the big question, though, is, I glossed over this here, but how do you compute those gradients for a deep network? Right? Doesn't seem that easy. So, for logistic loss, say, or the support vector machine, and a linear classifier, we derived what the loss looked like, and what the gradients looked like. Right? And it wasn't too hard because we had a linear function. We had a loss function applied to a linear function. We could use like a chain rule like one time and figure out how to compute those gradients. With a deep network, and remember here, theta here means the set of all the different weights, the different layers. So the first layer weights, second layer weights, etc. What this actually means, we actually need to compute gradients with respect to all those things. So the one with gradient with respect to the first layer of weights, second layer of weights, etc. And these are now multiple composed functions that we are trying to figure out the gradient of all of them simultaneously, right? Which seems like a hard thing. But the good news is that there's actually a really easy way to do this, and this is actually what's called the backpropagation algorithm. So the backpropagation algorithm for neural networks is just a way to compute the gradients of all the parameters efficiently. And it turns out, really what it is, it's just an application of the chain rule from calculus, but it also involves some things like proper caching of intermediate terms and doing the multiplications in the right order, so you have the small size vectors the whole way instead of big matrix multiplications. But that's all that backpropagation actually is. It's just sort of a formulaic form for applying the chain rule of multivariate calculus to compute all these different gradients here. And what's really nice is that you don't actually ever need to implement it yourself either. So this has been an innovation that's happened literally in the past 3 or 4 years. What's happened is that all these software frameworks have come about. These are things like TensorFlow or PyTorch or MXNet and others. All these frameworks have come out that let you actually automatically compute gradients if you just specify the forward pass, the forward kind of computation in your network. So rather than having to compute what, and they go through all this effort of computing gradients with respect to all the parameters, I just kind of define what the network looks like in terms of, I multiply that by this matrix, then I add this thing, then I multiply this, then I apply this on a linear function, then I multiply this matrix, etc. If you specify just that part, these frameworks let you then actually compute gradients automatically. They use a technique called automatic differentiation. And you will get to play with them a little bit on the homework if we can get them installed in Autolab in time. I think last time we used Theano, which I would rather not use because it's deprecated right now. It's not really being maintained anymore. So I'd rather use one of either TensorFlow or PyTorch. But we're going to have to see if we can use it for your homework assignment or not. But even if you can't, a lot of people are doing this for the tutorial or for their project. So they're very easy frameworks to use to basically quickly be able to compute gradients, and that's what enables this explosion in deep learning, is the fact that people don't have to compute gradients manually anymore, and so all that work you did for SVMs and stuff like that is no longer needed, and that was even the easy case. Okay, so that's a very, very quick overview. Of course, I didn't describe backprop at all, but it's essentially just an automatic way of computing gradients in these deep networks, and that's sort of the crux of it. What I want to spend more time talking about, just again, not that much more time, but very briefly, is talking about some specialized architectures people use for deep learning, and then finally, kind of bring us back to data science. Because I think this lecture so far has been very machine learning heavy and not very data science heavy. It's unclear how you sort of find real relationships in the world with things like this, but I want to bring, or whether you even need this for most data science. But I do want to bring it back to data science in a second. Any questions first, though? No, I'm going fast. I have a lot of slides, so I'm going faster than normal, I know, but still do feel free to stop me and ask questions. Okay, so let's talk about specialized architectures. And really, what I should emphasize here is that this wave of deep learning is actually not at all due to what I showed you so far. These sort of matrix multiplies followed by other functions followed by more matrix multiplies. What it's actually been based upon, so this includes the ImageNet winners, that the Go player, and the translation. They're all based actually upon two more complex types of architectures called convolutional neural networks and recurrent neural networks. So from a very high level, convolutional neural networks are basically applied to, well, they can be applied to actually to a lot of things. But the basic idea of convolutional neural networks is that, if I have like a 256 by 256 RGB image, that would be, 20,000 dimensions in my input image. If I take a matrix and multiply, by that entire thing and create 1,000 features, that's already, 200 million parameters of my network just for that one matrix multiply. Because every term in the matrix, right, mapping that size to 1,000 outputs would be its own parameter. And so this is going to probably do a lot of things. A, it's not going to be that expressive because this is just this is like the first layer of a linear function, right? Let alone many layers. It's not going to be that expressive, and it's going to require a huge amount of data because to fit that many parameters, we need a huge amount of data, and so it's going to be pretty likely to overfit. So the problem here is the generic network doesn't capture any of the natural invariances that we see in images. So an image, if we shift the image over by a pixel, it doesn't really change what the image is. If we zoom out a little bit, it doesn't really change what it is. What this is doing is sort of ignoring all the structure in an image, treating it like, and it doesn't also capture the fact that there's locality in images. Like these pixels here are more related than this pixel and that pixel, right? So there's all this there are all these relationships and invariances of images that we want to be able to exploit in an architecture. And what we're doing, if we just treat it as a vector, is sort of having one linear function of this whole thing mapping to this one linear function of this whole thing mapping to that one, et cetera. And we don't want to do that. So what the idea of convolutional architectures is we're going to do two things. First of all, we're going to have each subsequent layer be a function of only a small number of previous layer, pixels, for example, right? So if we have an input image here, say it's black and white, so just one channel, and say just one channel in the next layer as well. What we're going to say is that this element here is going to be a function only kind of these pixels locally here, and so it's going to sort of preserve locality of the images. And we're going to say that the weights that sort of combine on these pixels to form this weight are actually the same as when you slide these things over along the image. So this is an operation known as a convolution, and you basically keep the same weights as you slide these filters over your entire data set. It's also common to use things like what are called max pooling. So you basically take, if you want to decrease the size of your receptive field here, you decrease the size of your image, of your sort of effective image in your network. You can do things like set this one here to be the max of these four pixels or something like that. Now I should say actually what we really do is we actually do sort of blocks of these things. So you may have 3 input channels for an RGB image. You combine them to form another channel, kind of pseudo-like channel in your next layer of your network. You combine them in a different way to form, another channel of your network. And so these get kind of complex, but still they have much less, much fewer parameters than you would have if you were to just sort of treat this as a big dense vector. The other things that are important is that despite all this this complexity here, convolutions are still linear operators when they boil down to it. So they are just actually like a very structured matrix. And so it turns out this enables you to do things like backpropagation, computing the gradients in a very effective way. It doesn't actually change the structure of what we saw before. It just makes those matrices very heavily structured rather than arbitrary matrices. The other big type of network, and I guess I should sort of say that these these convolutional networks they probably have been the biggest kind of driver of the adoption of deep learning techniques. So they've had some of the biggest successes, namely image classification or just lots of stuff with images as a whole, and secondly, things like the Go playing program, the AlphaGo program that beat the world master at Go. Okay, so the other type of network that's been very influential are something called recurrent networks, and these have been really influential in the domain of sequence modeling. So, I've so far talked about prediction tasks largely as being, from one big kind of static set of inputs to a small dimensional output or something like this. But when you have a task like translation, like machine translation, right, you actually have multiple outputs you want to predict. So my input is, a sentence in French, and I want to output a sentence in English. So there's no notion of taking all that and making a yes or no prediction. It's actually a very complex object you're predicting, and you're doing this in kind of a sequential fashion because you want to preserve the fact that this is actually a sequence of words that makes up this sentence here. Now, predicting each element independently would of course be impossible. You can't do translation of a language by translating each word individually. It doesn't actually work. Or you can try, but you get very, very poor results. And so these sequence models are actually very helpful in kind of preserving information about the actual sequence themselves. There are lots of examples of things that benefit from sequence methods, so like time series forecasting, sentence labeling, part of speech tagging, as I said, translation, etc. And in this sort of domain of predicting sequential data, the structure that's been most used is what's called a recurrent neural network. So these are networks that are kind of like normal neural networks, except that they actually also propagate things forward in time. So you have your inputs, and instead of your inputs being just sort of constant at all, so this is the first layer here. Instead of that being constant over all time, you actually have the first layer at time 1, at time 2, at time 3. That goes to the network to form the next layer. But you also have kind of connections between these temporal layers, and with some kind of interesting kind of dependencies there that get very complex if you want to get complex. And in fact, even this is not quite enough in practice. People do things like very specialized architectures that sort of preserve interesting state over time. So one of the more well-known architectures people use in recurrent networks is called a long short-term memory network, or an LSTM network, which basically takes input and produces output in a very complex manner that I definitely will not get into here, but you can read more about it or look at figures like this to try to get some sense of what it's doing. Okay, so again, no real details there. The big high-level point is that the advances that have happened in deep learning are not due to big, multiple, matrices that are fully dense, stacked one after the other in a big network. What's actually happened is people have developed very clever architectures based upon convolutional and recurrent networks that are able to be sort of specialized for tasks like image classification or Go playing or machine translation. And that's really been the breakthrough that's happened in the past 6 years, or the breakthroughs that have happened in the past 6 years in deep learning. With these two types, the convolutional and the recurrent networks being the most commonly used examples of these advanced architectures. Okay, so I finally now want to get back to data science. Because really this is, obviously at a different level, but this is the kind of the same material I teach in an AI course, which is, I think, separate from data science in very notable ways, right? So where do we use deep learning in data science? So, I mean, first of all, it might be that some data science positions are really just machine learning positions, and you're going to be working on state-of-the-art deep learning no matter what, and that's great. You should probably take a machine learning course or a AI course in addition to this one to sort of get familiar with that. However, I think this is important to emphasize that I do think that deep learning, even as sort of practiced by novices, to a certain extent, can play a big role in data science. And so I'm going to give a very quick take on why I think that's the case right now, with the time I have left here. So if you remember my first, the first lecture we had, I talked about the sort of the set of all problems we want to solve, right? How some of the problems were were simple. They could use simple machine learning. Some of them were unsolvable, and so we'll talk actually a few lectures from now how to differentiate between those two types of problems. It's a very important skill. But there was this sort of narrow gap here about problems that needed, for example, deep learning. And these are things like, as I said, computer vision, machine translation, these really important problems that are kind of at the forefront of AI, but which are not really the standard data science problems you typically get in industry, right? People don't want to solve general AI to figure out how much more of their product they should make or not. They just want to sort of analyze data in a rudimentary way to understand what decisions they should make. And so I sort of said that maybe 5% of the problems needed deep learning. And this is sort of again a completely arbitrary set of numbers here. I'm just making these up. But I actually now want to emphasize that what I really kind of mean here in some sense is that this is what I was really talking about was this is the things that require kind of new deep learning. Okay, so it turns out that a lot of these simple problems can share some characteristics with more complex ones. So they can, for example, have things like image data associated with them, right? So maybe if you want to predict, the value of someone's house, you could just look at their square footage, stuff like this, their, how many floors they have, bedrooms they have, et cetera. Or you could look at a picture from Google Street View of their house, right? Which seems to have more information than just the stats of their house, right? So there are a lot of cases where it seems like we actually could take kind of simple data science problems and add very complex additional sensing modalities that somehow give us more information. Okay, and this is actually a big trend in data science these days, precisely because of deep learning. Okay, now the important part here is you can make use of this without necessarily, or definitely without, needing to develop brand new deep learning methods from scratch. Okay, so the idea here is that when you come up against some machine learning problem, sorry, I actually have one thing to say first. So before I get to this next part, is that what I'll say first is that when you come up against a new problem you're trying to solve for the first time, don't apply any of these things first. Okay, so don't include image data as the first thing you do, and then try to predict from image data, how much a house costs or not. Okay. That shouldn't be the first thing you do. The first thing you should do would be to get the basic features, the square footage, the number of stories, this kind of stuff, and run simple methods to try to predict that. And then see where those things are kind of still making mistakes, and see if those mistakes can be corrected by the addition of these more complex features. All right, so things like either more complex algorithms, or actually adding things like visual images and then applying deep learning. So the idea is don't apply, deep learning does have a place in data science, but don't apply it first. Definitely try the simple things first and then apply deep learning. That's point one. Second point is that when you do have data like this, or when you try to add data like this, so either if your data really is just visual data, or if you want to specifically add visual data because you think it's a feature that you will benefit from, now you can apply techniques from deep learning. But very importantly, unless you really know what you're doing and have a lot of data and a lot of time, don't try to train a deep learning model from scratch either. What you should do instead, you should take what are called pre-trained models. So these are the models that train on things like ImageNet. Or other similar data sets, and apply them as is to your image data. Okay? And then instead of looking at the final classification, you look at the layer right before that final classification, like the last layer of features kind of from these models, and treat those essentially as features for your problem. So what you're doing effectively is you're using a deep network, an already trained deep network, as a generic feature extractor for your image data or your sound data or your text data. And this is how you should apply deep learning for the most part in data science. So it's not about training new algorithms. It's about taking existing off-the-shelf models and and using them as feature extractors for things like image data or sound data or text data. So a very common example, and this is actually, despite the fact that there are better performing networks than this one, this is actually still a very common one to use in a lot for sort of this kind of feature extraction for a lot of reasons. There's sort of a very famous network called the VGG network that was actually wasn't even a winner. It was like second place, I think, on ImageNet, but it was considered for a lot of reasons better than the first place one for some of these type of things. But the idea here is this is just a sort of a normal network that's trained on ImageNet. So it's trained on 1 million images of, you saw them like container ships and dogs and cherries and stuff like that. And the amazing thing that seems to be the case here is that despite the fact that this network was trained on dogs and ships and mites and things like this, if I apply it to look at images of houses, it does surprisingly well. So I can take this exact same network, apply it to an image of a house, and then treat the last layer of weights, basically this one down here. So this is you have all these convolutional layers, you have fully connected layers, the matrices. You take the very, very last one before the before the 1,000 way prediction of what class it is, and you just look only at those that vector for a given image, and treat that vector as generic features. Treat that as your normal phi of x, right? And then learn a linear classifier based upon those features. That appears to work very, very well. It's still kind of a mystery about why it works so well. We don't really understand that from a theoretical standpoint. But there seems to be this great amount of transfer we can do where the features or the structure of a network, the weights of a network learned for one domain seem to transfer well to other domains too. You can't use it exactly, of course, because you're not trying to find dogs in your picture. But everything with the very last layer seems to be really good at doing everything but just dogs, and then the last layer seems to be good at dogs. That's not quite true, because there are some intermediate things that are still specialized for dogs. There's a lot of dogs in ImageNet, by the way, so this is why we always use the example of dogs. And you might actually want to do things like fine-tune the network, it's called, where you sort of do a few more sort of gradient steps to do this. But this seems to work really well. Now, the important part about this is the reason why you do this instead of just training from scratch is that typically you will not have enough data to train one of these things from scratch. So remember, this took 1 million images to train these things to start off with. If you are collecting data about housing prices and you want to use Street View images, you will not be able to easily get, you could, but you don't want to collect 1 million images of houses before you can do anything, right? And you will need 1 million images if you just train it from scratch. So the benefit here is if you do this, you now have a vector of 4,000 features or so that I can use as just generic features that now I need much less data to actually train a good classifier to do well on that. So that's the idea of these things. The same applies, by the way, to text processing. I gave this example already, actually, but text processing with Word2Vec. It's a very similar thing, actually. So Word2Vec is a nice model. It actually is a simple deep network kind of, or it's actually not even that deep. It's a simple neural network structure. But the idea is you should not train your own Word2Vec model. You should find a pre-trained model trained on a huge amount of text, and then apply that to your own text data set when you want to analyze text. Same for audio. There are open source audio models that work that you should use instead of training your own audio model from scratch. So in all these cases, the point of deep learning and data science is that these are areas where you have the ability to incorporate very complex sensing modalities and types of data into your pipeline. But the way you do so is not by training these things from scratch. The way you do so is by actually taking pre-trained networks and treating them like generic feature extractors. So you don't even have to worry about deep learning. You just worry about features. We know how to deal with features, and treat your deep learning methods, for the most part, as kind of generic feature extractors, at least, again, for the first version of what you do. OK, so that's actually all I want to talk about deep learning. Again, the homework is going to be postponed to next week. The tutorial is due a week from Friday. We'll talk more about that next week. And I think that's all this. I guess the homework's due tonight. So good luck with that.